Interaction in a statistical model allows for a much better understanding of the relationships between variables. Interaction effect can be viewed as "it depends" effect. For instance, if someone asks you, "Do you prefer to wear a raincoat or a sweater on a cold day?" your response would probably be, "It depends on whether it's raining or not." In this case, the clothes is one variable, while the precipitation is the other variable in the interaction term, and it affects your preference for wearing a raincoat or a sweater. This shows the "it depends" nature of an interaction effect, where you can't answer the question without considering the other variable in the interaction term. Let's compare a model with to a model without interaction to better understand the advantages of using interactions. Both models explore whether we'll earn more money as we age and see how a profession choice affects our salary. And the model without interaction clearly states that as we age, our income increases by the average of 15K. And when we choose the IT job over the industrial job, we'll earn $21,000 more. So far, so good. However, the model has a problem. Salary increases with age regardless of profession, resulting in identical differences of 15K between young and old in both job classes. Similarly, IT professionals earn 21.3K more than factory workers at any age, young and old. This seems unrealistic, right? This occurs because models without interactions examine the influence of each predictor while holding all other predictors constant. While this is fine, it does not offer a deep understanding of how our income depends on both job type and age at the same time. In contrast, a model with interactions looks at the effect of one predictor at each level of the other predictor, which provides many more insights. For instance, for the young, a choice of profession is of great importance, as they can earn more in IT than in the industrial job. While as people age, the difference in income between the two types of jobs becomes less significant. Similarly, industrial jobs tend to have a noticeable increase in salary with age, while IT jobs do not. This may seem disappointing for the IT crowd, but we must remember that IT folks earn a lot from the very beginning of their career. If you are still uncertain about the usefulness of interactions in models, consider this. Which model would you trust to design your professional life? The one with interactions or the one without? The choice is yours, the consequences lasting. No pressure. By the way, if you stumbled upon this video and some words or code are unclear, I highly recommend watching the introductory video on emmeans package first. For now, let's return to our model and point out 3 important nuances. First, if we ask for estimated marginal means in only one of predictors, let's say age, we'll get a red warning that our results may be misleading due to involvement in interaction. Which seems like a problem, but it is actually not. The effect of age is now studied for different job classes, and the warning helps us to remember that. Therefore, when interaction is involved, do not interpret the main effects separately. Secondly, the difference between the young and the old people is negative because the income of older workers was subtracted from that of younger workers. If this seems counterintuitive, we can simply reverse the order within the pairs to obtain a positive number. And finally, did you realize that emmeans have 95% confidence intervals, while contrasts do not? Don't worry, I have you covered. We can display them using the infer equals true argument. The interaction between a categorical predictor and a numeric predictor, or covariate, is even more intriguing, as it produces even more results. Specifically, we can estimate and compare the slopes for salary changes over a lifetime for individuals with varying levels of health using the mtrans function. Here, the salary of individuals with merely good health hardly changes over a lifetime, as indicated by the non-significant slope. On the other hand, the salary increase for those with excellent health is significant. The contrast between the two slopes also reveals a significant difference. However, the problem with this difference in slopes of 0.8 is that we still don't know how much more people on the blue line would earn. Moreover, the plot shows that this difference changes with age and cannot be expressed as a single number. The cof-reduce equals range argument solves this problem by measuring the difference between blue and red lines at minimum and maximum ages. This reveals that young people earn roughly the same amount regardless of their health, while older, healthier individuals will earn over 53K per year more at the end of their career, which is significant. Well, being healthy and rich at 80 might sound like a dream come true, but let's face it, it's probably not gonna happen. Most older folks are retired and can't make that kind of money. So, to spice things up a bit, let's make the numeric variable non-linear, since that's often how it goes in the real world. But the problem with this more realistic approach is that non-linear relationships can't be summed up as slopes. Fortunately, we can use specific values of age using the emmeans function. Check this out. If we use the cof-reduce false argument with emmeans function, we will be able to see all possible values of age. This gives us a complete overview of our data and enables to choose fewer, more meaningful values of age to compare to. The add equals list argument allows to specify exact ages. Let's, for example, take 25, 45 and 65 years, representing the beginning, middle and the end of a career. And all of a sudden, it looks like we are comparing two categorical variables, with age having 3 categories and health having 2. As a result, we can again create 2 different types of contrasts. The first is between specific values of the age covariate within each level of health, and the second type of contrast can be examined between health levels at any particular value of age. Therefore, if somebody asks you who earns more, very healthy or less healthy people, you would have to respond that it depends on their age. Namely, young people earn the same regardless of their health, while older individuals with very good health definitely earn more. You can't certainly answer the question about salaries in different health levels without knowing the age, because it depends on age. So, since the relationship between things in real life always depend on something, models with interactions tend to be more realistic. Then how does an interaction between 2 numeric predictors work? Pretty easy actually. Having the option to select specific values of numeric predictors gives us a valuable tool for easily modeling and interpreting interactions between 2 numeric predictors. It's crucial to choose only a few key values, as plotting all the numeric values of both covariates could be overwhelming and chaotic. Again, having the full picture gives us an advantage as it allows us to choose the most meaningful values for both numeric variables. From there, we can treat those specific values as categories and easily obtain estimated marginal means and the pairwise contrasts between them. I think it's quite remarkable that we can interpret a model with 2 interacting numeric predictors that have a nonlinear relationship with a response in such an understandable way. Let me know in the comments below what you think and whether you know a better way to interpret such models. Treating interactions as it depends effects enables us to model higher order interactions also, like a 3-way interaction which involves 3 variables in the term, for example age, job class and health, where the relationship between which and any of the predictors is entirely dependent on the other 2 predictors. For example, the relationship between money and health depends on job class and age. As we can see from the reference grid of our model, there are many combinations you can get contrasts for. You can essentially compare every error bar on the plot to any other error bar. Here are just a couple of examples. But wait, you may suddenly realize that you now have a different problem. While models without interactions have limited results, models with interactions provide too many results, even with only 2 or 3 categories per predictor. Imagine the results if one of the predictors had 5 categories. Fortunately, there is a solution that allows for presenting these results in a more compact way. For that, and in order to be more realistic, let's actually consider the education predictor with 5 categories and have it interact with job class. Even with only 2 predictors, we'll get so many estimated marginal means and contrasts that they won't fit on a single computer page. One of the most effective ways I found is to put all the results into a matrix. This matrix displays the estimated marginal means along the diagonal, p-values in the upper triangle, and differences in the lower triangle. For example, the estimated marginal means for individuals who did not finish high school are 85 for industrial jobs and 88 for IT jobs. The salary difference between them and their peers who did finish high school is 16K per year and is not significant for the industrial job class because the p-value is 0.16. You get the idea. And since one picture is worth 1,000 words, the second effective way to present a lot of results is to actually visualize them, where we first visualize the estimates with contrasts using this simple plot command and the argument comparisons equals true, and then plot all the p-values using the pairwise p-value plot. Now that we know how useful and informative interactions can be, the only thing left to learn is how to find the best model which includes only meaningful interactions. Fortunately, GL Multi package allows you to do just that with a few lines of code. And if you want to find out how, check out this video.